Replacing embedded resources in the world of HTML, we are used to creating links to images, scripts, and style sheets. However, in APIs it is uncommon to see these kinds of static resources exposed. With careful use of client-side private caching, an API can efficiently expose static resources for all kinds of information that would normally be embedded into a client application. Indirection layer links are used as a way of providing a layer of indirection. By creating discovery documents at API entry points, we can enable clients to dynamically identify the location of certain resources without having to hard-code URIs into the client application. See Example 6 to 11. Example 6 to 11. A Git Hub discovery resource get https://api.github.com/ current to 0 https://api.github.com/user authorization so https://api.github.com/authorizations emails https://api.github.com/user/emails emoji so https://api.github.com/emojis event so https://api.github.com/events user search https://api.github.com/legacy/user/search/keyword. This layer of indirection allows a server to reorganize its URI structure without clients needing to make changes. Imagine that Git Hub wanted to allow searching for users by location. It could make the following change. User search https://api.github.com/legacy/user/search keyword country. Assuming the client was following the rules of URI template RFC 6570 token read placement, there would be no client changes necessary to adopt this new URI format. We can also use indirection to provide a type of intelligent load balancing. If certain resources are putting a disproportionate amount of load on a server, the URIs could be changed to point to alternative servers with additional capacity. This can be useful when different types of requests create very different types of workloads. Indirection can also be useful for finding geolocated resources. Using client location based on IP address, response representations can contain links to servers that are geographically close. This can be very important because network latency can be a significant factor over long distances. Accessing a server on the east coast of the US from a client on the west coast will likely be on the order of 80 milliseconds. When there are numerous resources to be retrieved to render a user interface, this can quickly be very noticeable to an end user. Reference data. It is common in data entry user interfaces to provide the user a list of options to select from. These lists don't need to be predefined in a client application, and in fact a client doesn't even need to know in advance what list needs to be associated with a particular input field. By annotating an input field with a link to a list of options, a client application can generically identify the valid list of items without any knowledge of the input domain. For example, /Canada. HTML forms achieve a similar goal by embedding the entire list into the input element, but that is not a particularly efficient approach. Links can be used as a way to reduce payload size. Sometimes certain pieces of information are required less often and can be moved off into a distinct resource. You can often offset the extra cost of the second round trip with the savings from not retrieving the additional information when it is not needed. A second reason for splitting resources is when the volatility of the data is very different. Retrieving a representation of sensor readings from a device that includes all the device configuration details is wasteful because the sensor readings would likely change far more often than the device configuration. Adding a link to the device configuration enables us to retrieve device configuration information only when needed. The third reason for splitting resources is to enable reuse. This is the case in our address / province list example. The list of provinces is the same for any Canadian address. If a user is entering many addresses, then being able to use a client cached copy of the list can be very effective. Workflow. Probably one of the most unique features of REST-based systems is the way that a cation workflow is defined and communicated. In RPC-based systems, the client must understand the application interaction protocol. For example, it must know that it has to call open before it calls send and close when it has finished. These rules have to be baked into the clients, and any dynamic detection of state must be built ad hoc. Links, embedded into representations, can be used to instruct clients of the valid actions based on state. A client must still be aware of the types of interactions that exist in order to use them, but it no longer has the burden of knowing when it is allowed to make a certain type of request. Consider example 6 to 12, a version of the same scenario using hypermedia. Example 6 to 12. Using hypermedia to define workflow get / device API 200 OK content type application / HALX. Post / device API / sessions content length 0. 201 created session content type application / HALX null location http / example.org / device API / session / 1435. Delete / device API / session / 1435 200 OK. The client still needs to understand the open / send / close link relations, but the server can guide the client through the process. The client must know that to activate the open link, it should send a post with no body, and to activate the closed link it must use the delete method. In this example the responses use HAL, but there is no reason the server could not return more than one hypermedia type. The link relations do not need to constrain the returned media type. It is necessary, however, that the client understand at least one of the media types returned by the server. If a client is designed to understand that links may be dynamic, then it can adapt to changes in the workflow. For example, if it used an algorithm where it first looks for the send link, if it does not find one it looks for an open link, follows it, and looks once again for a send link. With this approach, if a later version of the API does not require the open / close dance, then the initial / device API representation can be changed to immediately include the send. The client would automatically adapt to the new protocol and continue working without change. This is an extremely simple example. More complex applications have more complex interaction protocols and more opportunities to take advantage of this dynamic work. Flow capability. Syntax IFC 5988 also specifies the format for embedding links into HTTP headers so that even with binary content like images and video, you can still include hypermedia with the returned representation. What is not specified, however, is how links should be embedded into other media types. The way links are serialized must be specified by the media type specification itself. This is another reason why using media types like application/SYN and application/XML can be problematic, as they don't define how links should be represented. There have been a number of different conventions used, but without a hard spec it is difficult to write reusable code to parse links. It would seem like a trivial thing to define, but I've seen people debate for hours over whether HSYN objects should be called links or links. Here are some examples of link syntax. Application/HSYN. Links. Self-ref/orders. Next ref/orders. Page equals to, find. Ref/orders, ID, template true. Admin. Ref/admins/to, title thread. Application/collection links. Real blog, ref http://examples.org/blogs/sto, prompt blog. Real avatar, ref http://examples.org/images/sto, prompt avatar, render image. Application/bnd.github.v3json. Assigning. Login Octocat, ID1, Avataro https://github.com/images/error/octocavapi.gif. Gravataric summer hex code, URL https://api.github.com/users/octocat. Application/HALXML. Application/atomicsml. http://www.example.org/images/icon. Text/HTML. Ref equals http://cdn2.static.net/stack overflow/or.css. V equals C9B143E6D693. Fac. Placeholder equals search to index equals 1 type equals text. Maxlength equals 240 size equals 28 value equals. As you can see from these examples, links can take on many shapes in hypermedia representations. In the coming years, I hope we will see some more convergence on styles to remove some of the cosmetic differences. It is worth noting that although many of these examples do not have a real attribute, they have the notion of a link relation type. In the case of HTML, an tag could just as easily be represented as. The same argument can be made for representing a tag as. Placeholder equals search to index equals 1 type equals text. Maxlength equals 240 size equals 28 value equals. The two styles simply demonstrate two different ways of identifying the link relation semantics. They also introduce an interesting workaround to one problem some people have with link relations as defined by RFC 5988. In order to use a simple token like real equals destination, you must register this relationship with IANA, which means there will be a review by domain experts. The intent of this registry is to encourage the development of link relations that are suitable for use across many different media types. As mentioned earlier, you can use the notion of extended media types and create a link relation that uses a URI. However, URIs can be long and noisy in representations. If you want to create a link relation that is specific to your particular media type, then you can choose to use a serialization such as by making the link relation type an integral part of the media type syntax. You are explicitly stating that the link relation is defined only within this media type, and you can avoid the URI naming requirement of extended link relation types. There is another interesting property of link relations. Links can have multiple relations assigned to them. For example, be aware that this capability is simply a serialization optimization. It does allow the behavior of the links to be combined. RFC 5988 says, relation types should not infer any additional semantics based upon the presence or absence of another link relation type, or its own cardinality of occurrence. Semantically, there is no difference between the previous example and the following. RFC 5988 also defines a number of other metadata properties of a link that can provide information to the user agent on how links should be processed. Instead of being specified in a written document, the instructions can be embedded in the representation of the link. These attributes are simply hints to the user agent. They do not guarantee the server will provide compliant representations. A perfect combination link relation types and media types are the peanut butter and jelly of the distributed application world. Link relation types bind together resource representations to create a complete application that allows users to achieve their goals. These contract types work best when your semantics are evenly spread between them to encourage serendipitous reuse. Designing a new media type